So I want to start by thanking the organizers and for inviting me and for putting this together, and also the other speakers for the nice talks so far today. I'm really sorry that I'm not able to be there in person, but I look forward to your questions, and also if anyone wants to follow up with me by email to set up a time to chat about anything I discuss, I'm happy to. Before I get started, I just want to point out that while we're getting the opportunity to participate in this really nice conference, every single university in Gaza has been destroyed. And I just want to remind everyone that our Palestinian colleagues, including fellow particle physicists and astronomers, and their communities deserve to live in dignity. So as a Jew whose family survived pogroms and the Holocaust, I want to ask you all to think about what it would be like if it was your family and take action accordingly. So to get to the point of my talk, there are two things. So some of you may know me as one of the three topical conveners for the SNOMAS Cosmic Probes topic, along with Alex Derlica-Wagner, who I heard was in the audience, and Haibo Yu. And one of the points that we really wanted to make to the community is that astrophysics is an essential probe of particle physics. So I think from looking at the results of the P5 report, we see that that point really did come across. So what I'm hoping as we start to move forward into this era of large surveys with so many different experiments happening on the astrophysics side, as well as planning ongoing on the particle physics side, is for people to start thinking of these topics as in conversation with each other and not really separate, both from the point of view of actually doing the science and also for anyone who might be involved in funding on the funding side too. I also want people to take away the point that scalar dark matter is a thriving area of research. So I think I'm the first person to talk about this today. And what you're looking at here is a figure from the SNOMAS 2014 report. I want to show you just from the Cosmic Frontier chapter from SNOMAS 2021. So this is a really nice figure that looks at the different ways that we can explore things that broadly might fall in the category of scalar dark matter. So this figure is based on content that appears both in the CF2 and CF3 chapters, as well as an overview in the Cosmic Frontier chapter. There's an archive number on the bottom. So one of the things that I want to highlight is that we're in this really exciting time for scalar dark matter. There are a lot of different ways that we can come at it from a ground-based experimental approach. And the thing I wanted to highlight, and we worked really hard to get this point across, is on the bottom I have this thing circled. Cosmic Probes covers a huge mass range in terms of what we can explore and learn about scalar dark matter. So as we move forward into this next decade of incredible surveys, there is a lot in the parameter space on the theory side that we can start to really dig into, and cosmic probes are a key role in doing that on behalf of particle physics as well as in conversation with particle physics. So this is just like a quick outline. I don't have a ton of time, so I'm not going to spend a lot of time getting into the outline. We all are at this conference because we generally have some sense of how dark matter shapes our universe. But I will just say that a particular emphasis for me over the last few years has been this question of the galaxy halo connection. So looking at distributions of dark matter and trying to understand how those distributions of dark matter are reflected in observations of visible matter. And one question in particular that I've had is how is the axion, if the axion is the dark matter or scalar dark matter more broadly, imprinted potentially in these series of statistical connections. And of course, this figure is taken from a really nice review by Risa Wexler and co-authored by Risa Wexler, who I'm sorry to not be seeing. Hi, Risa. And I also want to point out that something that doesn't get discussed as much in this context is also that people have been thinking about neutron stars as dark matter detection facilities. And when we think about what our next generation telescopes are going to be doing, we should not just be thinking about optical, infrared, and UV. We should also be thinking X-ray for a variety of reasons, not just for the purposes of neutron stars, but also including neutron stars. And neutron stars are not just interesting because of the ongoing debate about the galactic center excess and the questions of what exactly is happening there, but also because we have these questions about what the composition of neutron stars actually is. So I think we want to think broadly as we move forward about what we think of as cosmic probes of dark matter and what scales are potentially involved there. Okay, so I'm going to skip the animation there, as nice as it is. Getting into the question of what is dark matter. So obviously, I think a lot about scalar dark matter, and in particular, I think from the place of axions. So I've been focused on real fields as opposed to complex fields. I'm happy to talk shop with anybody about the details of this. Here's a really nice Venn diagram from the late Ann Nelson about why axion dark matter theories, broadly defined, are actually really nice dark matter candidates. So as she pointed out, these are natural and elegant theories. They are also viable theories. So essentially, you can think of this as something that comes naturally with the model building that we're already doing in particle physics, for example, to solve the strong CP problem. And it's also something that doesn't break physics as we know it, which is always nice to not have to revise everything, but rather we can add axion dark matter in quite naturally and, as Anne put it, elegantly. So I just like to remind people that when we talk about scalar dark matter, axions, axion-like particles, ultralight axions, fuzzy dark matter, there's a lot of nomenclature out there that I think can be quite confusing for people. There are also these questions of whether axions count as cold dark matter. So my answer to that question is yes. And I refer to non-axion CDM as vanilla CDM. So that's just the way that I think about it. That's something we could debate, I guess. So the distinctions to be made here, QCD axions are really the Pesce-Quinn mechanism axions. So these are formed in the early universe, so very high redshift. And these are expected to be about 10 to the minus 5 EV in mass. There's a broader class of axion-like particles, ultralight axions, and fuzzy dark matter. So these models are often motivated by string theory. They don't always solve the strong CP problem. And the key thing that connects all of them is that for cosmological purposes, we can typically describe all of these as scalars, so bosons, with a sinusoidal potential that gives a Lagrangian of the following form. So I will just highlight for people here, the spite of the 4 term has been, I think, a point of understated contention. Has been an area of focus in my work. So I'm going to come back to that. So I just want to identify that for people in the audience. So I'm talking, in some sense, the results that I'm going to talk about today apply broadly across all of these classes, but there are points at which the distinctions matter. For example, if you're thinking about CMB power spectrum, if you get beyond like 10 to the minus, I think 28-ish EV, if you go down below that, then you're no longer in the realm where it can be 100% dark matter, but you can also be thinking about interesting combinations or transition points between dark energy to dark matter models. So given that we have this situation where it's interesting, dark matter is often framed as a particle physics problem and not an astrophysical problem. For example, when you're talking to funders or when you go to big astronomy conferences, yet our only evidence for the existence of dark matter comes from astrophysics, right? So of course we should be asking the question of, can we use large scale structures to distinguish between these various models of dark matter that we have? And of course, a particular question for me is, can we use large-scale structures to look for evidence of axion dark matter? I'm going to say I use large-scale structures in a very hand-wavy way here. What I'm calling large-scale structures, you might more technically call small-scale structures, but to a particle physicist, it's all very big. So 10 years ago, the question that we were all asking ourselves was, does axion dark matter form Bose-Einstein condensates? And really what we were trying to understand here was, if you look at this really nice figure from the Shue papers that I think a lot of us have now seen from 2014, this question of whether in the core, as you get into the core of the halo, you get these coherent, what we've been calling in the literature, soliton-like structures. And so this is something that I also thought about back when I was a postdoc. And there's a question of what governs the scales involved in these structures. And so we showed that you can get something that's Bose-Einstein condensate-like, with a QCD axion, they're actually going to be quite small. They're going to be like asteroid sized. And the bigger lesson here was that the sign of the self-interaction, so that lambda in the phi to the 4 term, along with the mass of the particle, is going to determine the coherence length. And this is really just the lower mass the particle is, the longer the de Broglie wavelength. And so you're going to get a larger scale. And so, of course, people have become quite interested in ultralight axions because essentially you can have these halos with solitons at their core. In this case, in the particular Shiwei paper, you see that there's a scale of 5 kiloparsecs here. So this core here is 0.96 kiloparsecs. This is assuming a particle of 10 to the minus 22 eV, which I guess I could say there's a lot of literature that suggests that this mass has been entirely ruled out. There is at least one analysis that shows that when you take the self-interactions into account, those restrictions weaken a little bit. And it's notable that all of the analysis that's been done by the Shiwei team really focuses on a fuzzy dark matter model where there are no self-interactions. So the field is treated as a free field with no phi to the 4 term. So there have been a lot of questions here, and I actually think that it's easy to get really to just kind of run away with one picture and hand wave and not think a lot about the details. And so my particular take and approach to research on this has been that the devil is in the details. So there has been some discussion in the literature about whether the evolution of this scalar field is purely a classical mean field theory or whether it has quantum components. For example, when the particles are changing in energy level, because there is not strong interaction with the electromagnetic field, how does the system shed energy? How does energy move around? It's not necessarily going to be thermal in nature. And so there are questions about whether this requires some kind of quantum analysis. There's also been a debate about when the self-interactions matter or whether the self-interactions ever matter. So you notice again, I have that phi to the 4 term here on the screen circled. And so that has been, so just to provide some context for people who don't think about this all the time, like I know some of the folks in the room do, and this lambda is going to be quite small. And so the natural assumption is that because this term is going to be so small, that you can just throw it away. You can hand wave it away. There's no way it can have any kind of dynamical impact on the system. So the flaw in this thinking is that actually what is of significance here is not lambda as a coupling term by itself, but lambda times the field density, so lambda phi squared. And here we're dealing with a scenario where the occupation number is very high. And so you can't actually just throw that term out because you actually may be throwing physics out. So this is not me saying that all of the research that excludes the phi to the 4 term is wrong, but rather we should be thinking about these as distinct dark matter scenarios, whether it's a free field or not a free field. There's also this question of actually how do we think about the collision process and the dynamical evolution of systems with axions. And so work led by my graduate student, Tony Mirasola, along with his co-PhD advisor, Kay Kirkpatrick. We have a couple of archive posts that were published in PRD that you can look at down here. What Tony helped us find was that we need to use the Wigner formalism, not the Boltzmann formalism, for understanding this. And originally, the reason that we were curious about this is because I wanted to understand the time scale for condensation and whether self-interactions would affect the time scale for condensation into these solitons. And what we found is actually that the self-interactions are subdominant. So you really do, to get condensation into a soliton on timescales that are reasonable for our universe, you actually really do need gravity. And this might make you think, okay, well, the self-interactions aren't important, but they are, it turns out, significant for the dynamical evolution of the system. So this was shown in work initially led by my former PhD student, now Dr. Noah Glennon. So what you're looking at here on the right is a scenario where a soliton is time stepped forward as it orbits a central potential. And so what you're looking at basically is the tidal stripping as you turn on self-interactions, and depending on whether they're attractive or repulsive, so the middle and bottom scenarios, you can see that the time scale for tidal stripping changes. You can also see, so here on the left, you have two solitons. So you can think of these as like subhalos that are dynamically interacting with each other. On the left, there's no self-interaction. On the right, there is an attractive self-interaction. You can see actually that you get completely different outcomes depending on whether that phi to the 4 term is there or not. So it really does have dynamical significance. We continued along this line of thought, and along with Ethan Nadler, who's one of the organizers, my postdoc, Dr. Nathan Musoke, who will be giving a talk at the workshop next Monday. So those of you who are staying, please go to see it. Along with Arka Banerjee and Risa Wexler, we showed that, so on the left, you have the attractive situation, repulsive self-interactions. These situations, as their time step forward, they seem to evolve and they look similar, but you can see as time goes on that the systems actually look quite different, and the tidal stripping looks quite different depending on whether the self-interactions are turned on or not. And depending on whether they are attractive or they are repulsive. So you can think of them adding or subtracting from gravity at different length scales is maybe one way to think about that. We also considered how self-interactions might compare with a no self-interaction scenario with dynamical friction. And so here you can see that as you move forward, you get a completely different wake, depending on whether there are repulsive self-interactions or whether there's no self-interaction. And I just want to highlight that all of these computations were done in a code developed by Nathan Musoke called UltraDark. And there's descriptions of them in the archive papers that have been listed at the bottom of the screen. So I will just say one open question that's come out of this work that we've done is that these effects have a mass and self-interaction degeneracy. So you can change the mass or you can change the self-interaction, and you can actually get scenarios that look dynamically identical with different combinations. So an observational problem that I think we have is how would we possibly break that degeneracy to know which situation we're in? So I was really excited by Tanya's talk this morning because I think that is the physical scenario and the observational scenario that we hope that this work will connect with. I also, since I'm low on time, I'm not going to talk about this a lot, but one of the things that we're now starting to think about is a multi-axion scenario where, for example, on the left here, you have one species of axion with two solitons. And on the right, you have two species of axion where they, in this particular case, we did the simplest scenario, they have identical masses. But they do have self-interactions. They also have interspecies interactions. And so we wanted to explore whether these systems would be identifiably and phenomenologically separate. And what you can see is even when we've tuned things to be as similar as possible, you get these interference patterns that look different, and the density distribution, as you can see in the center column, actually looks quite different too. So I basically used up all of my time talking about axions. So I'm just going to point to this work by my PhD student, Nathan Rutherford, who will be applying to fellowships in the fall. He's been thinking a lot about neutron star equation of state using the NICER telescope. It's a little X-ray telescope that lives on the International Space Station. So the ISS is an astrophysics facility. I just want to remind people it's not just there as an interesting space travel experiment. We do astrophysics there. And by looking at magnetic hotspots on the surfaces of neutron stars and reconstructing the space-time, so you can see here that there are distortions that we then use to reconstruct what the mass-radius relation of a neutron star actually is. That this can help us gain insight into what possible equations of state could explain the interior of a neutron star. So far, some of Nathan's work has shown that we can't prove from just these kinds of observations that dark matter is there. But importantly, what he's shown is that the presence of dark matter is completely consistent with the data that we have so far. which means that if we're not taking dark matter into account in our neutron star equation of state analyses, we may actually be excluding physics that is relevant to the systems that we are looking at. So as far as techniques that we should emphasize as we seek to answer these questions, I am a big proponent of the idea that high energy astrophysics is part of the future of high energy physics. I think as hopefully everybody knows, very unfortunately, NASA has made the mistake to begin to wind down the Chanda X-ray telescope. This is a problem not just for people who are interested in active galactic nuclei and other kinds of high energy astrophysical phenomena. It is a problem for the dark matter astrophysics community. And so I hope those of you who are writing to your representatives about saving Chandra are thinking about that in those terms. This matters for your science too, not just your colleagues. And for people who want to understand more about what's happening on this plot, I will just encourage you to pick up the Strobeck's white paper. It's on the archive. But we can place constraints on axions using X-ray and gamma ray experiments. And Strobeck's is a proposed high energy mission. It's being evaluated by NASA right now. So anybody here who happens to have a say in that, please consider Strobeck's. We're really excited about what it can do. I will stop here. I will just say that I'm the one who got to give the talk, but there are a lot of different people who contributed to the things that I talked about. So I'm just part of a team, and I'm really grateful to every team member. Thank you for listening.